So basically, this lecture is going to be a little bit less mathematical than the previous ones, in that the goal here will really be to discuss feedback in complex systems more generally. I'll also kind of come back to the a sort of attempted definition of what we mean by complex system, because I don't know if you've noticed, but so far I've carefully avoided actually defining what a complex system is, right? I gave you the definition of a dynamical system, but that's really just a mathematical concept, so it has a very clear definition. We'll see that complex system doesn't really have such a clear mathematical definition, so we'll get back to that in a bit. So, okay, so this is something that I've shown you a couple of times before, right? This is the Bretherton diagram, which is a sort of broad diagram that was, it was designed by NASA to study the Earth system. So the idea, the way to read it is that every arrow here is an interaction between subparts of the Earth system. So what do we mean by the Earth system, basically? So the Earth system is the atmosphere, the upper layers of the crust, so the soil, really, and the oceans. So, for instance, the internal, the mantle of the Earth, and which drives volcano activity, that's not considered a part of the Earth system in this diagram. This one's considered external, right? And in the same way, energy coming from the sun is an external influence. So the way to read this is that all of this here, this is the Earth system, and these are just external driving forces, right? And these are the subparts of the Earth system, and they interact with each other in a, I think you're probably aware of at least some of these interactions, right? So for instance, the interaction between atmospheric chemistry and physics and ocean dynamics. So you're probably aware of, for instance, the fact that increased carbon dioxide emissions has led acidification of the oceans, which then means changes in marine biochemistry. So we'll have some time to discuss that again, but that's something you might already be aware of. You're almost certainly aware of the effect of carbon dioxide on atmospheric physics, right? In that it increases the greenhouse effect, and thus the global temperature. Right. So the idea is that in a system such as this one, you have many different interacting subparts. You have external driving forces, so volcanic activity and solar energy, and all of these subparts have different feedback systems built into them. So I'm going to, first of all, have a quick recap of what we saw last time, right? So we studied nonlinear systems, and in particular, we saw the difference in response to external driving between linear and nonlinear systems. We saw that basically, if you have a linear system and outside driving force, a linear system will respond simply by damping down or increasing the effect of certain frequencies in the driving spectrum, right? Whereas a nonlinear system has the ability to respond in a way that's not proportional, and also potentially to add different frequencies to the response spectrum. So I'm going to quickly go back to remind you of what I mean by that. So if we had, for instance, we had the example of a nonlinear effect in sound treatment, right? So for instance, if you have a saturated amp, that's a nonlinear effect. So it cuts out the crests of your signal, and that means that instead of responding at the same frequency as the input signal, you add frequencies to the spectrum, right? So this is the original frequency is just here. This is the sine wave, and as you cut bits of the sine wave in your nonlinear system, you end up having additional frequencies coming up in the spectrum, right? Which is the equivalent, it's like when you shout and your voice goes hoarse, right? There's added richness to the sound of your voice precisely because you're going into the nonlinear regime of how your voice box works, basically. Okay, so what the link with chaos, right, was that it is precisely that the appearance of new frequencies in the system that means that the response of a chaotic system to outside driving can become very complex, right? Because it'll add additional movement to the initial driving force. Okay. Chaos can occur as a result of structural instability. So this is something that we discussed a few times with the logistic map, for instance. So you remember any dynamical system, it has variables, but it also has parameters. So just numbers which describe the interactions within the system. So for instance, in the logistic map, we had this starvation parameter, which dictates how fast the population dies off when there's overcrowding. And we saw that variations in this parameter could qualitatively change the behavior of the system, going from periodic to chaotic, for instance. Okay, so that's what we did last time. And also, we had a quick look at the difference between transient and steady state response of a dynamical system, right? So as you recall, we were looking at the way in which, for instance, an oscillator can be driven by, for instance, a motor or something like that. And when when you switch on the driving, there will be a point at which stuff happens. There is behavior that is transient in nature, meaning that it only lasts at the beginning of when you switch on the driving, and then dissipates. So an example of transient behavior, for instance, would be if you knock an oscillator, then what it'll do is it'll start behaving like that, right? So I think we saw if this is the amplitude of the oscillations and this is the time, then it'll do something like that. There we go. So in the absence of any external driving, this is the transient behavior. So you knock the oscillator, it oscillates a bit, and then there's damping, this dies out, right? So transient behavior dies out after a while, but the question here will be how long, right? Because obviously transients just mean that it eventually dies out. In the Earth system, there are transients which last for 10,000 years, right? So obviously they're of interest, right? And so far last time, we only really saw the steady state response. So this notion of like transience versus steady state will be important in this lecture. Okay. So what we'll do today really is first of all define feedback. What it is precisely that we mean by feedback. I mean, feedback is a word that is very much overused, right? In that really now it's come to mean just reply, or you give me feedback just means respond. So feedback is a slightly more precise term in physics. We'll also distinguish between the different types of feedback, positive, negative, and we will give examples of feedback in the Earth system. So going back to the Bretherton diagram there, we'll take up just a few subparts of this system and start studying what happens, right? And in particular, as regards climate change, basically. Okay. Then what we'll see is that we'll link this, so we'll see how feedback links to the general question of stability, right? Does a system have a stable behavior, or does it actually become unstable? Can it be destabilized, for instance, in the same way that the population evolution with the logistic map had a solution where it suddenly became very chaotic? So this question of stability will be approached through the lens of feedback, and also we will see how basically linear and nonlinear systems have a different, respond differently to outside perturbations, and will basically give some kind of explanation as to why it is that actually almost everything we see in nature has some nonlinearity built into it, right? And we'll see how that nonlinearity is both a source of robustness, in that essentially if your heart, for instance, were not a slightly nonlinear oscillator, then it would probably be subject to all kinds of perturbing influences. But on the other hand, the fact that it is nonlinear also means that in certain regimes it can become chaotic, right? So we'll see that nonlinearity in a system with feedback is sort of a double-edged sword, right? It can be a source of stability, or it can be a source of chaos, depending on what you're looking at, really. Okay, so the last thing is that we will be drawing a little bit from the study of feedback and system response in engineering, because basically these are really, engineering is really the place where these concepts were first developed, right? We can take a sort of like figurative view of things, and when we draw block diagrams like this, like the Bretherton diagram, we can, basically here we're sort of taking an architect's or an engineer's point of view, right? We're saying, if I had designed the Earth Earth, these would be the subsystems I'm thinking of, these are the interactions I think exist between these subsystems. But this is very much, an engineer's point of view, right? Obviously, the Earth isn't actually quite so well, divided into neat little subsystems, right? So the slight detour via engineering will allow us to sort of see where all these concepts originate from. Feedback as a concept very much originates from 18th and 19th century engineering. Okay, so again, I've sort of been talking about complex systems for a while and avoided defining them. There is a reason for that. So this is one of the textbooks that I've used for this course, right? It's called simply The Dynamics of Complex Systems, and it begins rather amusingly with this sentence: we do not expect it to be possible to provide a succinct definition of a complex system. Instead, we give examples of such systems and provide the elements of a definition. It is helpful to begin by describing some of the attributes that characterize complex systems. Complex systems contain a large number of mutually interacting parts. Even a few interacting objects can behave in complex ways. So if we pass this, basically what does this mean? Quite simply, there isn't really a rigorous mathematical definition of what a complex system is in the way that there is for a dynamical system, right? Dynamical system was very straightforward. A dynamical system is a system that has variables, parameters, and a dynamical equation. That's it. Whereas this complex system is a less mathematical concept. And basically what he's saying here is, what's a complex system? I don't know. I know when I see one, right? And you can see that he introduces some basic idea. He says, well, a complex system has many parts which interact with one another. And as soon as that bit's over, he contradicts himself, right? He says, but actually, even a few interacting parts can behave in a complex way. So maybe we can still call a complex system, we can still call something with simple dynamical equations a complex system, because as you recall, and this has sort of been one of the leitmotifs, right, of this lecture course, is that even something as simple as the logistic map, which had a one-line dynamical equation, that could behave in very complex ways. So it's actually, it's actually unclear whether you would call the logistic map a complex system or not, because it certainly doesn't have many interacting parts. It has, one variable and one parameter. That's not many, right? So basically, the sort of rule of thumb we're going to use, and this is kind of what I've been using for this course really, is, well, what's a complex system? Anything behaves in a complex fashion. And it can behave in complex fashion because it consists of lots of different interacting parts, or it can behave in complex fashion because of chaos. But here, we'll mostly be looking at systems which are actually quite complex, just in how they're subdivided into parts, right? So we'll be looking at the Earth system in particular. But before we get to that, we'll go through a few examples of more simple feedback and also define precisely what we mean by feedback. Okay, so feedback is a description of interactions between different parts of a system. But it's not just interactions. Really, it's interactions where you take the current state of the system, and information from that current state is, well, fed back into the system to modify its dynamics. Meaning that, if I knock a pendulum and it starts swinging, there's a response, clearly, but that's not feedback, right? Nothing about the state of the system that I've modified here is going to be feeding back into the dynamics, right? Feedback, well, we actually had an example very early on in this course of something in a physical system that kind of looks like feedback, right? Which was simply a falling object subject to air resistance, where in that case, when a falling object accelerates, as the speed picks up, friction increases. And as friction increases, acceleration decreases, and eventually you have some kind of balance, right, between the friction forces and the gravity and the gravitational acceleration. That you could almost already call feedback, right, because the current state of the system, how fast it's going, is being fed back into the dynamics, so the forces in play are modified, and eventually you end up with a sort of steady state response of the system, which is just, your object falling at its terminal velocity. So okay, so really, feedback, so this is my definition. I think it's reasonably broad, and I think it really does capture the basics of it. So you have information about the current state of the system, which modifies the dynamics of the system. So it's not, feedback is not just response, right? This is just how we use the word in sort of like common language. So, as we saw, feedback is really an engineering term. It was designed, well, it first came up actually, not even quite in engineering, but in political economics, basically. The first people to use the term feedback in the 18th and 19th century were primarily economists, so people like Adam Smith or philosophers like David Hume. So feedback can happen by design, as in engineering, or as a result of natural interactions, which is what we'll describe right here with the falling ball problem. Right. So this is the first system we can look at. This is some guy dropping a basketball from a dam. And we've already kind of studied this dynamical system, right? And I've chosen it because it's particularly simple, but it still has a few interesting features. So you remember, from a dynamical systems perspective, we had defined the variable of this system, which was just the evolution of the ball of the speed. The system itself was just the ball of mass m. You had a few parameters. So parameters of this, we had the gravitational field constant. We had a friction parameter, which I'm going to call little f. And we had, obviously, the mass of the object, m. And we got to the dynamical equations like that. So simply, if you recall, we have Newton's law. M, so rate of change of velocity is equal to minus g, g minus f v, and that's it. Right, so this was the dynamical equation we came up with. This can be read, in plain English, right? The rate of change of the velocity is equal to mass times the gravitational field constant minus the friction parameter times the speed. So the aspect of this which looks like feedback, right, is that you have the current state of the system. So this is the current speed at time t. This will give you the rate of change of the speed. So this gives you information about the future state. And what happens is you can just write, do a little drawing. So if the initial speed is small, so this is the initial speed, then you have a very small friction term and a very large gravitational acceleration term. So this is friction. And as the gravity increases velocity, so we now have larger velocity, so friction becomes larger, gravity is still the same, and eventually we get the impression, we get intuitively the fact that eventually these two will balance out, right? Friction and gravity will balance out, and you will reach what's known as terminal velocity, right? So if you were to look at this from the perspective of an engineer, you might call this a kind of feedback, right? I think for a system that simple, we wouldn't actually bother, but you can still have a look at it in this way, right? Where you can have some kind of block diagram, right? Which is, you have an increase in speed, then you check, is the speed smaller than the terminal velocity? And if it's smaller than the terminal velocity, then you go back here. If not, so yes. And if not, you come out. So you can view this very simple physical system as a kind of feedback, right? And in particular, you can also imagine what would happen if, instead of just dropping the ball like that, so I let it drop, it's reached its terminal velocity, and I whack the ball. So now the speed increases slightly. So as you'd expect, what happens if you have a speed that's larger than the terminal velocity? Well, in that case, friction is now higher than the acceleration due to friction will be larger than the acceleration due to gravity. And so, as you'd expect, if something bumps into the ball and puts it here, it's just going to decrease back and go back to its terminal velocity. So this is interesting. This is where the idea of negative feedback might come into play, right? Is that ultimately what it does is that you want to keep the system at some kind of constant velocity, and you have some kind of interaction, some kind of feedback that allows you to kick back to put back the ball in the desired state, right? This is obviously not a state that you've engineered, but something very similar will happen for engineering, for engineered systems. The kind of question you can ask yourself about such a system is, well, how long will it take for the system to reach the steady state, right? Obviously, in the case of this ball, right, you have this would be the transient response, and this is the steady state. So steady state is just the ball is going at a constant velocity, and we might ask, if this was an engineering system, we might ask ourselves, well, okay, if I knock my system about a little bit, how long will it take to return to the state at which I want it to function? And obviously, the question is not very relevant for a ball, but for an engineered system, it's very much a question you want to answer, because you want your system to come back to the state where it's supposed to be functioning as quickly as possible, but as quickly as possible without inducing instability, which is something we'll see later. Okay, so that's the kind of question you can ask. How long will it take to get to 90% of VF, 99% of VF? Because you'll notice as well that this is an exponential curve. It doesn't actually ever reach the final terminal velocity. It only asymptotes towards it. Yeah?
The steady state, does that mean that the system has now entered linearity?
Pardon?
The steady state,
yeah.
Does that mean that the system is now linear?
No. Steady state can be in a linear or nonlinear system. What steady state means just means that the variable is no longer changing. So at this point, V doesn't change anymore. So a steady state just means that you've let the transient response die out, and now you're looking at the way the system is going to behave over, for the rest of time, quote unquote. Okay, so that's a very simple example, right? But we can already have a look at actually what is a slightly more complex, at a more complex example, this time which is very much an engineered system, right? So this is an escalator. So I don't know if you've noticed with escalators, they tend not to accelerate or slow down as people get on them or get off them. But obviously, it takes more work to lift 10 people than does 7. So the question is, when these 4 guys over there get off the escalator, how comes these 2 people are not just suddenly accelerated upwards, right? Because if the escalator was just a motor turning with constant, working at a constant rate, then as soon as these people get off, they would just start going faster, right? And obviously we don't want that, right? So a real escalator has all kinds of feedback built into it. And we can see it in a very schematic way, in this way, right? Is that you have some kind of input. So this is the speed of rotation of the motor underneath, for instance. So the actuator is just the motor. It converts the electrical signal into movement. And then what happens is that information about the current state of this actuator is being fed back. So there's a sensor that detects how fast the motor is rotating, and that sensor feeds back information to the system. And what it does is that if it senses a deviation from the correct rotation speed, say like you want 1 rotation per second, and it senses that now these people have gotten off. So for a very brief instant, the rotation speed increases. We're now at 1.5 RPS. Well, what the sensor says is that, well, we've exceeded the desired speed. We're going to just decrease the input, and the actuator will slow down. So the motor will slow down. The rate of work will diminish. And this is. So there are different ways of doing this. You can so the sensors in this case will simply be like a dynamo, for instance. So a dynamo is just a little thing that rotates and creates an electrical. It creates voltage as it rotates. So the idea is that you can imagine that there's the main motor putting the escalator into motion, and a small dynamo which just keeps measuring the rate of rotation. And as soon as the dynamo feels that as soon as these people get off, the dynamo accelerates. So now the voltage of the dynamo has increased, and that information is fed back into the system to say, if the dynamo's voltage has increased, decrease the voltage of the actuator, of the big motor, right? So this is just the very simple, this is a big picture, right? But now there are obviously some actual, some precise engineering issues which we'll need to address here, right? So for instance, if it was the case that the response time was very, very fast, But you could imagine that the system would overcorrect, right? If it was just, if the motor just had an on-off switch, for instance. So this is kind of what happens with a thermostat. So to control temperature in a room, usually what you have is you have a thermometer, you have a heater, and a feedback system, where if temperature exceeds, say you want your thermostat at 25 degrees, temperature exceeds 25 degrees, the thermostat just sends the information, and what happens is that your heating will just shut down for a bit. And then as soon as it goes back down, it turns the heating back on, etc. So this is feedback with a very simple on-off state, right? This is obviously not going to be the case here, right? Because you can imagine what would happen if, these people walk off. Now the sensor says, oh, the escalator is going too fast. It just switches off. Well, sure, the escalator is going to slow down again, but it's going to slow down brutally, and these two people are probably going to trip over themselves, right? So that's the question of transient effects, right? Do we want, do we want the change to be brutal, and in particular, do we want the response? We want the response time to be both fast, so that so fast response time means that at no point will the escalator speed vastly exceed or be less than the speed we want it to go at. But also, we don't want this to lead. We don't want a fast response to lead to instability. Where, for instance, you could also imagine that the escalator overcompensates. So someone steps off. It says, "Oh, we're going too fast now," so it slows down brutally. Then the sensor says, "Oh wait, we're going too slow now." It goes back, it puts back some work into it, and you can imagine a state that would be unstable, right? Where instead of converging towards a steady rate of rotation, actually the escalator just goes like that. It keeps kind of going faster and slowing down, and that's obviously not a desirable feature here. So these are very generic questions that you can ask of any kind of engineered system with feedback, right? How quickly does it respond? What kind of transient effects do we have? So are there oscillations? Do they die down quickly or do they not die down? So that goes to this question of stability. Are we actually going to ever reach the point which we want to reach, or are we just going to oscillate to and fro between two extrema? And obviously these are very practical questions for engineered systems, but you can ask more or less the same questions of a natural dynamical system. So, these two things, by the way, these are both examples of negative feedback, right? This is negative feedback, this is also negative feedback, right? In that you want the difference between the desired velocity and the measured velocity to be as small as possible, so you have negative feedback. And here's a case of positive feedback, and you'll see, there's a very good reason why most engineered systems don't have positive feedback built into them. Okay, so the situation is one that we probably all know, right? So, there's an epidemic. The way an epidemic is defined is you give what's known as the R0, which is the average number of people that a given person will infect, right? And here I've used the very simple toy example. Imagine a flu epidemic where every single person will just infect 2 other people, and that person becomes immune within a week. And the idea also, we're going to assume the total population is much larger than a few thousand, so that we can ignore effects of mass immunity, right? So this is very much a toy model. Obviously, real epidemics will behave in much more complex ways. But let's see, let's see what kind of prediction we can already get from that, right? So basically, you all know how to solve this problem, right? You just take 2 times 2 times 2 times 2 times 2, and you can check that 2 to the power of 10 is 1024. So if you go after 10 weeks, you'll have 1,000 people, and then after 11 weeks, you'll have 2,048. So this is also something which always has to be borne in mind when studying systems with exponential growth, right? Is that I don't know if you've heard this one. This is a very famous example of how to think about exponential growth. So imagine there's a pond, and that pond contains water lilies, and the number of water lilies just doubles every day, right? And we know that on day 30, the pond is entirely covered in water lilies. At what day was the pond half covered in water lilies? Yeah, exactly. So day 29, right? So this is something because we tend not to think too much in terms of these exponential growths. Our intuition is trained on linear growth. So we want to say, well, day 15, obviously, but obviously not the case here. Okay, so how is that positive feedback? Well, basically what happens is that the current state tells you how many more infections you'll get next week. So information about the current state is used to compute the number of new cases, and then the number of new cases becomes the number of current cases, because we said that anyone who was infected previous week is no longer infected, right? So this is possibly the simplest possible positive feedback loop we can imagine. The number of current cases is just directly fed back to get the number of new cases, and that just loops around like that. In a very generic sense, anything that has dynamics that looks like that is going to behave in an exponential fashion. So this is an exponential curve. Here it's just y is equal to 2 to the power of x. So you can check that 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, etc., etc. Such a curve has a property, so exponentials have the property of being proportional, so the value of the exponential at any point is proportional to the rate of change of the exponential. What does this mean concretely? It's it's called the Matthew principle, which is the rich get richer and the poor get poorer, right? So if you're over there, then your rate of change will be very fast. If you're over here, your rate of change is very slow, etc. going here. So you understand immediately why that positive feedback is going to be a destabilizing influence, right? Because the more you have, the more you get. And here, this is for comparison, this is actual data, right? So obviously, this is just a toy model, this is just a mathematical function, but this is actual data, right? These are new case numbers for COVID in Italy in 2020. As you can see, it very much, at least for the first few weeks, it very much follows an exponential curve, right? So even a very simple positive feedback model is pretty effective to deal with predictions of at least the first phases of an epidemic. Okay, so we've seen three different systems. These two were negative feedback, meaning that you end up becoming more stabilizing around a desired value. Here you have positive feedback. Positive feedback, on the other hand, will mean exponential growth. And we can already start, so we can now classify these things, right? Now, negative feedback is obviously very prevalent in engineered systems because we tend to want our systems to converge towards a desired value. We don't really want them to run away, right? So negative feedback is present in natural systems, but very much in engineering systems. Positive feedback, on the other hand, because it increases the effects of the perturbation that gives rise to it, well, that will tend to be destabilizing, right? So there are natural systems which do contain positive feedback, and we'll see a few of them in a bit. But overall, this is going to be a destabilizing factor. And you can also see, you can begin to sense how that will have something to do with chaos and sensitive dependence on initial conditions, right? You recall that was one of the definitions of chaos, was this sensitive dependence. Now, if we go back to the number of cases here for the epidemic, we can ask ourselves, what happens if I missed a few patients this week? So that week, I just, for some reason, I missed out on 2 or 3 cases, right? So the initial difference is going to be very small, but as you can see with exponential growth, the difference is going to grow very large very quickly, right? So for instance, if you take the example of the power of 2 law, right? Well, imagine you thought that initially there were only 2 cases. So you know that on week 10 you'll have 1,000. But actually, if you only missed 2 people, there were actually 4 people who were already infected, that on day 10 you'll actually have more than 2,000 cases. So an initial difference of 2 patients on your first week will actually be a difference of 1,000 people infected in your 10-week prediction, right? So this already hints at sensitive dependence, and we'll see that indeed it has something to do with it. Okay, so that is one of the questions, right, which we can now seek to ask about these different types of feedback. It's quite simply, how will uncertainty in the current state translate into uncertainty in the future state? And we'll also see, maybe, if we have time, strategies to avoid the pitfall, right, of being thoroughly misled into believing predictions which are wrong due to sensitive dependence. But this, I'll maybe say a word or two about it towards the end. Okay, so that's the first question, uncertainty. The second question will be, well, okay, so we know that feedback acts in time, right? And we hope that it acts to stabilize the system, for instance, but we want to know, okay, how fast is it going to go back to the desired value, right? How long does it take for the escalator to respond to the fact that there are fewer people on it, right? So we want to know what the transient response looks like, what the steady state response looks like, because we've seen that if our feedback loop is a bit dodgy, we might actually have a steady state which oscillates instead of converging to a desired value, and that's obviously no good. Right, and well, that's really a question which is to do with this one. These two are linked, right? How fast do the feedback mechanism kick in? Okay. So now the next few slides are really about concrete examples of feedback systems within the Earth system. So we're not going to look at the Earth system as a whole, we're going to look at certain interactions between its subparts. Because as you remember, the Earth system is very complicated. It has some aspects of it have to do with atmospheric chemistry, others are atmospheric physics. We have the biosphere will obviously have a massive impact on all of these changes. So here we're looking at one particular system, one particular subsystem, which is affected by something called silicate weathering. Silicate weathering tends to be a long-term effect. So this will modify the Earth's temperature, for instance, over hundreds of thousands and millions of years, right? And the way it works is this. So silicates are so these chaps are silicates, right? They're rocks that contains silicium, which has an atomic symbol Si. So sand, for instance, is a silicate. Quartz is a silicate. All of these things are silicates. So they make up a very large proportion of the Earth's minerals, right? And silicates can react with carbon dioxide in an acidic environment, and they will give rise to what's known as hydrogeno-carbonate ions, and these ones will react with calcium ions in the sea to become carbonate rocks, right? So the starting product is silicate rocks. You end up with carbonate rocks. Carbonate rocks they're a kind of light limestone chalk. The shells of marine animals tend to be carbonates. Actually, this is what chalk is, right? So chalk is just a ground down shell powder, basically. Okay, so the idea is that this is a way for the Earth to regulate its carbon dioxide atmospheric content. Because what happens is that you start out with carbon dioxide in the atmosphere, and this is brought into a chemical reaction with the silicates, and by the end of the process, the carbon is caught into these carbonate rocks, and these just get dumped at the bottom of the ocean. So the net effect of this is that with silicate weathering, as silicate weathering occurs, the concentration of carbon dioxide in the atmosphere will decrease. Typically, it will decrease over timescales of around 100,000 to a few million years, right? But this is a process to draw out carbon dioxide from the atmosphere. This is the key thing. So, in what way is this an actual feedback loop? Well, the idea is that this chemical reaction, right? So the chemical reaction which takes silicate rocks and turns them into carbonate rocks via reaction with atmospheric CO2, this reaction is actually sped up as the temperature increases. So let's start reasoning about this, right? So imagine we have, an early Earth, lots of carbon dioxide in the atmosphere, and as a result, much higher greenhouse effect, right? So we could go something like that. CO2 has increased, which implies that temperature has increased. This is just the greenhouse effect you all know about. Now the temperature increases, silicate weathering is going to go faster. So silicate weathering now increases. So silicate weathering increases its rate. If silicate weathering increases, then you're drawing out more CO2. So CO2 decreases. So this is atmospheric CO2. And well, what's going to happen is that eventually this now means that greenhouse effect decreases and temperature decreases again. This is something this silicate weathering system was used amongst other things to explain something that was puzzling geologists and biologists for a very long time, which was how did the Earth develop life at a time where the sun was much less brighter than it is today, right? Because this is the thing, so the sun is what's known as a main sequence star, which means that it evolves over a few billion years. It goes from being fairly faint and fairly cool to being hotter and hotter until eventually it'll become some kind of red giant, right? But the point is that when life started out around, I think the rough order of magnitude is like a billion years, I don't know, I'm not a biologist, but something like that, right? So a few billion years ago, as the Earth was still young, the sun was much less bright than it is today. So you would think that that would induce the temperature to be much, much lower than it was today. And life just wouldn't have been able to cope with that temperature, right? So the silicate weathering allows you to understand why it was that you could still have a sort of like reasonably hot temperature on Earth despite having a fainter sun. Because we can do this thing in reverse, right? If the temperature decreases, silicate weathering will decrease. If silicate weathering decreases, then CO2 will increase, and therefore the temperature will increase, right? And the way that CO2 is brought into the atmosphere is just through volcanic activity. So there's a constant source of CO2 in the Earth system, right? So this is interesting, right? This is a stabilizing negative feedback loop, basically. This allows you to explain why it is that the Earth's temperature can remain fairly stable over the course of hundreds of millions or billions of years, despite the fact that a lot of the driving influences of the Earth system have changed. So the sun's temperature could have changed, volcanic activity can change, and obviously these days we're emitting lots of greenhouse gases, so that changes as well. So you might simply ask the question, why won't that just work for us, right? We keep banging on about how we need to stop emitting greenhouse gases, but if there's a system which just naturally draws carbon dioxide out of the atmosphere, then why bother doing it ourselves, right? And the answer is obviously, well, that works, but it works over a few 100,000 years. We'll be gone by that time, right? So we can't rely on that sort of stuff to save us in the short term, right? But this is an important point, though, right? That we have a negative feedback loop with a stabilizing influence, but the time scale over which it acts is very important because ultimately it's not the only feedback loop on Earth, right? So every time we look at subparts of a system, we need to look at the response times, right? We need to look at the transient features, even if we know that even if we think the Earth's steady state is going to be, steady temperature, steady CO2 concentration. Well, if it takes 100,000 years to reach that steady state, that's no good for us. Okay. So that's the silicate weathering system, which tends to stabilize temperature. There's another system, which this one illustrates positive feedback. So this is what's known as a snowball Earth scenario. Obviously, this is an artist's impression, but this is something that actually this is something that was first puzzling scientists in, I think, the 60s and 70s, where basically when we started running climate models, so climate models with very simple physics, right? We just have, we have some basic atmospheric physics, some basic interaction with the sun's incoming radiation, and the question was, okay, if we make a simple climate model, does it have an equilibrium state, basically? So in some way the question was, is there even such a thing as the climate, right? Can we actually say that there's an average behavior for the Earth which represents some kind of physical equilibrium, right? Because if you think about it, the Earth can be very, very simply represented as a kind of, you have the ground here, you have atmosphere here, and you have, solar radiation that is incoming here. Some of it gets bounced back, some of it goes through, this bounces back here, some of it bounces back again, some of it goes through. And you know that these things will depend, these will regulate the Earth's temperature, these interactions. So the first question we'll ask is, okay, so how much of the sun's radiation just bounces back from the atmosphere? Right, so as it turns out, for UV radiation, most of it. But for visible light, we know that it mostly crosses. It heats up the ground. When you heat up the ground, you end up emitting infrared radiation. That goes back into the atmosphere, bounces back. So this is the greenhouse gas effect here. But obviously the nature of the ground here is going to matter, right? Because if you have, for instance, and this is something that you will know if you know, on the same day with the same outside temperature, the same sun luminosity, you go into a city street which is full of concrete and it's really, really warm, and as soon as you go to a place which is greener, which has like higher albedo, as we'll see, then this decreases. So in particular, there were the idea being that if this is an ice shelf, then most of the radiation is being sent straight back, right? If this is concrete, most of the radiation is being absorbed and is going to be used to then heat the atmosphere. So this is a process that's known as, this is a concept that's known as albedo, right? So albedo is just how much, for a given surface, what proportion of the energy of the sun's energy are you reflecting back? So when albedo increases, that means that more solar energy is reflected. For instance, the moon has a fairly high albedo, which is why it appears to be white. On Earth, roughly the sort of ice shelves have the highest albedo. Sand has decent albedo. Ocean has very low albedo. It really very much does absorb the heat, etc., etc. So why am I talking about albedo? Because obviously this is a dynamic effect, right? Because if, for instance, temperature increases, and Arctic and Antarctic ice sheets decrease. So you now have these white caps on the top and bottom of the Earth, which are decreasing. That means that the albedo is decreasing, right? Because you have less surface that's able to reflect sunlight back towards space, right? So when people were modeling these effects, right? Effects of very, very basic greenhouse gases, well, very basic greenhouse effects, very basic albedo effects, and some broad, atmospheric and oceanic physics. These early climate models, they all had something in common, which is that one of the stable solutions that they found was just what was known as a snowball Earth, meaning that the Earth was just covered in ice and nothing happened. That was it. So people were quite puzzled, right? Because they thought that they would run their climate models and they would get something that looks vaguely like the climate of the Earth today, and that's not what they got. What they got was just the Earth freezing over, and that's it. Nothing more happens after that. So obviously, they deduced they asked two questions after that, right? A, is there actually a way for the Earth to come out of such a scenario? And also, did something like that actually happen, right? Are we do we think that at some point the Earth was really covered in ice? And the answer is yes. As far as I can tell, the geological consensus seems to be that there have been ocean snowball Earth events in the past, and we can have a look and see how that happens, right? With using positive feedback as a tool. So okay, the idea is here. We start out with some initial perturbation. Well, something happens, I don't know, cloud cover increases, or there's maybe, some kind of like volcanic eruption has clouded the skies. So the first thing that happens is temperature decreases. If temperature decreases, that means that, polar temperatures will get lower, and so you'll have the ice surface will increase. If the ice surface increases, albedo increases. So I'm calling albedo A. So albedo increases. If albedo increases, then you have more solar energy is reflected. So less solar energy is absorbed. And obviously, if less solar energy is absorbed by the Earth's surface, then that leads to the temperature decreasing. Temperature decreases, ice sheet grows, albedo increases, less energy, temperature decreases. So if this process becomes strong enough, this is what's known as a runaway process, right? At some point, there will be nothing to stop it, and once you've reached a tipping point, it will just cover the entire Earth in ice. And this is basically the reason that these models all have this kind of basic instability to them, right? Is that it doesn't take much. You can see that after a certain point, it doesn't really matter where your temperature started out. Once you start going down this route, at some point it will just grow without limit, well, at least grow until the entire Earth is covered. So this is a positive feedback scenario, and it has the effect of pushing the Earth system as a whole into a completely new realm, right? So you go from the planet as we know it today to a planet that's just entirely covered in ice. There's one thing we can add to this though, right, is that we know that actually the Earth has gone out of these phases, right? So we also know that actually, positive feedback can lead to runaway processes, but in a complex system there will always be some kind of thing that can counteract that, right? Temperature is not going to decrease infinitely, right? So this is something to bear in mind. Positive feedback processes can lead to runaway growth, but in a real system, runaway growth can never be infinite, right? So if we go back to the pandemic, right, we know that, for instance, this exponential curve, I've only shown you the beginning, right? Obviously, at some point, this stabilizes, right? At some point, you have effects linked to mass immunity or things like that, which will mean the positive feedback loop cannot go on indefinitely. In the same way, for the Earth system, at some point, the entire Earth is frozen, so temperature is not going to decrease any further, so you've stopped this runaway process. Once the ice sheet cover is total, T stabilizes, and when T stabilizes, what's going to happen is that actually, so volcanoes will still be able to pump CO2 into the atmosphere, because the volcanoes can actually, their emissions can go through the ice. So the point is that when what will happen is that CO2 gets pumped into the atmosphere, but because there are no visible rocks, silicate weathering, the thing we saw before, is no longer happening. So actually what's going to happen is that CO2 is just going to accumulate into the atmosphere until eventually the greenhouse effect melts the ice sheets again, and then you run the process in reverse, right? Temperature increases, therefore the ice sheet melts. If the ice sheet melts, the albedo decreases. If the albedo decreases, more cellular energy is absorbed, temperature increases, etc. So this thing can also run back the other way around, right? Which is unfortunately one of the issues with climate change today, right? Is that there's a certain question which is, okay, given how fast the ice sheets are melting, we don't know whether that might actually trigger a kind of tipping point whereby ice sheet decreases, albedo decreases, therefore temperature increases, ice sheet decreases further, and you might get some kind of runaway process whereby the Arctic and Antarctic ice sheets are completely destabilized, right, with only a few degrees warming. Though I think so. This is still unclear because obviously these are complex systems, but that is one hypothesis. Okay, so what is the big takeaway here, right? Is that anything that has feedback, and positive feedback in particular, will be prone to a kind of structural instability that we've seen in chaotic systems, right? Which is that you modify one parameter. So for instance, you've increased slightly greenhouse gases or decreased slightly greenhouse gases so temperature decreases. So you modify one parameter and suddenly the stable solution for your entire system shifts. Instead of being the Earth as we know it now, it becomes a snowball. Or other way around, it starts out as a snowball, and some kind of change in parameter means that it swings back all the way to being the way it is now. Okay, so here we've seen so far one negative feedback loop, which was silicate weathering, which is drawing out CO2 from the atmosphere over the course of a few 100,000 years. We saw one positive feedback loop, which was this ice albedo effect, right? And now we're going to see a case that is slightly more complicated because it actually contains both positive feedback and negative feedback acting on slightly different timescales, and which actually tell us some stuff about the way we're modifying the climate now, right? So this is what's known as the carbon dioxide cycle. So the question is, what we're looking at here are really interactions between the atmosphere, the ocean, and the marine biota, right? So the idea is that we're pumping CO2 into the atmosphere. And again, when we started noticing that we were emitting large amounts of CO2 in the atmosphere, that's back in the 60s, 70s, there was a puzzling thing about this, right? Which is that we were able to count sort of to count the quantity of CO2 that we were emitting, and then when we measured it into the atmospheric concentrations, for some reason, only about half of it ended up in the atmosphere. And so immediately the answer came, well, that's because when we send CO2 into the atmosphere, some of it dissolves back into the ocean, right? So the reason that the greenhouse effect isn't quite so strong as we might expect it to be today is because actually half of historical emissions of CO2 emissions into the atmosphere have been dissolved back into the ocean. So the idea is that you have this atmospheric CO2, which is in permanent equilibrium with ocean, well, with CO2 dissolves into the ocean. You can imagine, it's kind of what happens when you have a Coke bottle or something like that, right? Is that actually in your Coke bottle you have a you have CO2 that's trapped in a little bit of air underneath the cap, and you have CO2 that's dissolved into the liquid itself. What happens when you open it is that exactly quite. And you can see the reason for that, right? Because what's happened when you've removed the cap is that actually you've suddenly decreased the pressure above the liquid, right? So if the pressure decreases, it means that the chemical equilibrium that you had is being displaced. Now, the gas, the gas is now in excess in the dissolved form, and as a result, it'll just outgas, right? So typically you open the bottle and some gas comes out, sometimes a little liquid as well. Okay, so this is a very basic interaction. That's just, in terms of, you could write it as a chemical equation, and as a chemical equation it would really be terribly simple, right? It's just CO2 in gas form is in equilibrium with CO2 in its dissolved form. Now, CO2 in its dissolved form actually doesn't stay in the CO2 form. It very quickly becomes hydrogen carbonate, so HCO3-, which we saw in the acidic weathering, and that can react with the marine biota, right? What it'll do is it'll turn this CO2 into, you get this CO2 turning into CO3-, like this. It'll react with calcium, like that, and that gives you another equilibrium, like that. So this thing is what seashells do, right? So the CO2 was dissolved in the water, it gets turned through acid-base reactions into CO3-, and this thing reacts with calcium to get basically limestone, right? So or chalk, right? It's the same kind of rock. And this is what makes up the shells of marine animals. Which you've probably heard that one of the side effects of carbon dioxide emissions and of global heating is that as CO2 increases in the atmosphere, CO2 increases also in the ocean. This means that the oceans acidify, and this reaction doesn't happen very well if you had acid conditions, right? Which is one of the reasons you have all kinds of marine animals which now have very soft shells or can't grow shells properly, because this reaction can't happen in the acidic conditions of this CO2-rich ocean. Okay, so this is the basic chemistry, right, of it. So there's some interaction between ocean and atmosphere, which is just a dissolution equilibrium. Then there's an equilibrium which involves carbonate ions going from being present in the water to solidifying, right, precipitating to form carbonate rocks. So this thing here is the equilibrium described here. Then you have an equilibrium. This equilibrium here is this bit of the diagram, right? The rest of this we're not going to worry too much about. So for instance, we know that volcanoes will drive CO2 into the atmosphere. We saw that with the acidic weathering. There's obviously effects linked to vegetation. Vegetation will tend to draw out CO2 from the atmosphere. But we're not going to be looking too much at these parts. Really right now what interests us is just the ocean-atmosphere interaction, right? And our question is, as has been the case with the other feedback systems, okay, so what happens if temperature increases? Well, as it turns out, if temperature increases, this reaction happens less well. So as T increases, the equilibrium of this reaction gets displaced towards the left. So CO2 gas dissolves less. What that means, or at least it dissolves at a lesser rate, in lesser proportions, which means that if, for instance, at our current temperature, around half of CO2 gets dissolved into the ocean, but if you added 2 or 3 degrees to the Earth's global temperature, then that would decrease the proportion of CO2, of atmospheric CO2 that goes into the water. Now, you see that this is immediately a problem, right? Because if CO2 gas dissolves less, that means that you get more CO2 in the atmosphere. So more CO2 is left in the atmosphere. If there's more CO2 left in the atmosphere, well, I think we can all see where this is going. Greenhouse effect increases, temperature increases, so greenhouse effect increases, and temperature increases. So that's it. This is one of those bad feedback loops, right? This is a positive feedback loop, which means that as we increase the Earth's temperature, we decrease the Earth's ability to soak in the excess CO2. So this is quite bad. So thankfully for animals that will be around a few 100,000 years, maybe not us, there's another system which kicks into place when this happens. Basically, as I mentioned, when CO2 in the water increases, so when the concentration of dissolved CO2 increases, the pH of the ocean decreases. So which means that the ocean becomes more acidic. The thing is, if the ocean becomes more acidic, what happens is that it starts...
The water life gets affected, the fish and the life on water gets affected.
Yeah, exactly. So that's the first thing, is that this thing, when it gets acidic, these carbonate rocks, so for instance the shells of seashells, these will get dissolved back into carbonate, right? So as the pH of the ocean decreases, the acidity increases, carbonates dissolve. But here something nice happens for once. So carbonates dissolve, but carbonates have the ability to render the water more alkali, more basic, right? So as you release these things back into the water, then actually the pH will increase again. And as the pH increases, CO2 absorption, so oceanic CO2 absorption increases, and you start getting a virtuous cycle, right? After that, that means that the temperature will start to decrease. So in this case, you can see that there are two feedback systems working, there are two feedback mechanisms working within the same system. The tricky thing though is that this one responds very quickly. This one, you'll see its effect after a few tens, few hundreds of years. This one takes a much longer time, because you need basically the interactions between the deep ocean and the surface waters, and that typically occurs over a longer time scale. So this is one of the issues, right? What I was saying about transient effects, right? Is that yes, the steady state is almost definitely that actually a lot of the fast climate change that is happening now will get balanced out eventually by feedback mechanisms, but these are slow feedback mechanisms. Really, the ones that we're worrying about are these guys, because these guys are happening over periods of tens or hundreds of years. Okay, so this is just a sort of broad, right, so this is a summary. This is a summary of the first mechanism. So this is the positive feedback. And here is the second mechanism, which was the negative feedback that I was describing here. Okay, so time to have a quick sum up of what we've learned so far before we move on to a few words about engineered systems. So first things, as we've seen for the Earth system, in a truly complex system, you will get positive and negative feedback, which will occur around the same time. We see that broadly, negative feedback will tend to make the system converge towards a stable solution, whereas positive feedback will tend to lead to runaway growth of perturbations, which we can see already has something to do with the way in some chaotic systems behave. So we see that positive feedback can be responsible for the sensitive dependence that we were talking about at the start of the lecture course. And this here is an important point, right? So we saw that positive feedback can lead to runaway growth. But in a real system, you can't have runaway growth forever, right? Exponential growth exponential growth will eventually run into some kind of hard limit of the system, right? We know that, we know, for instance, that when as an epidemic spreads, eventually you will have infected most of the population and things will peter out again, right? In the same way that, for instance, if you had runaway growth in say you're looking at a feedback system which stabilizes some kind of motor, right? And your feedback system for some reason is screwed, right? It just goes into a positive feedback mode. So you perturb, so as the motor is perturbed slightly, instead of slowing back down and going back to its regular RPM, it just keeps accelerating, right? Well, eventually what's going to happen is just the motor's going to break, right? So positive feedback will stop at some point when the system is just destroyed, basically. So this is something that's important, right? Always keep in mind that positive feedback will eventually end, because eventually your system is just going to change its response entirely, which is what we call the case of the snowball Earth, right? At some point, the Earth temperature no longer decreases because you've just covered the entire Earth in snow. Well, nice. Okay, so which type of feedback dominates? That very much depends on the timescale, right? So you have to look at transient responses, right? Not just the steady state responses, which is tricky because typically when physicists analyze system response, they tend to really focus on the steady state stuff. The assumption being that we want to know what happens, when all the accidental effects have died down. We want the kind of final, the final response, right? But actually, there's a lot of information within this transient response, and even worse than that, right? In a chaotic system, there isn't any steady state, right? The chaotic systems are all transient, right? There's no at no point does the system really settle into something nice and quiet, which is incidentally a question that's often been asked of the Earth system, right? We don't really know the answer to that one, as far as I can tell. So basically, the question being, does the Earth system have a steady state, right? Is there such a thing as a kind of steady state climate for the Earth? And the answer is probably not, actually. It probably doesn't have, it will probably keep oscillating between, snowball Earth effect events to then, stuff that looks a bit more like what the Earth looks like today, to, a system where you'll get back to a high carbon dioxide and methane in the atmosphere, which becomes like a kind of hothouse Earth, as it's known. Okay, so that's actually a fairly deep question, right? In climatology and climate physics, like, can we even talk about a steady state for the Earth? Not clear. Okay, and this is just a final little remark, which is that indeed, even if you do have a steady state solution, it might actually be vulnerable to small changes in parameter values. So we saw that with the logistic equation, right? With this kind of very simple population dynamic model, which was that it did have a steady state solution in some particular cases, right? So for certain values of the starvation rate, the population would just oscillate in a very regular fashion, right? You'd have, rabbits breeding, rabbits dying, rabbits breeding, rabbits dying, right? But if you increased the parameter value, then suddenly the system's structure was changed, right? Instead of having the neat oscillation between 2 points, you ended up with having these sort of like rapid and random looking changes in rabbit population. Okay, so basically the question we're going to ask now is, well, so how do we quantify all that, right? How do you quantify stability? How do you quantify response time of the system to perturbations? And ultimately this is why we're going to be looking a little bit at engineered systems, because engineers have thought about this sort of stuff in a very quantitative way, right? Because they do actually want to answer the questions, how long will it take for my motor to settle, right? Will my steam engine just blow up because of some weird instability that is triggered by the feedback systems I've installed? And the advantage of an engineered system as well is that they tend to be much simpler than the Earth system, so that's a good thing. We can really make subparts and look at the interactions between these parts. And also, contrary to the Earth system, we can experiment on them, right? So the Earth system, we have one of them, right? We can't really, there's no reproducible experiment in climate science, unfortunately, which is why we rely so much on computer simulations. Okay, so this is a very, not even a history of feedback in engineering. This is like a few anecdotes, really. So this one I find quite funny. This is actually in a book on control theory, and it describes a little thought experiment by an 18th century engineer. So he says, so his most curious idea is the idea of the engineer in question. So a contrivance by which a horse driving a mill, or otherwise, should bring into action an automatic goad, so that if he did not pull with a certain force, it should prick him until he did. So what does this mean? You're a horse, you're drawing you're pushing the mill, right? And behind you is just a tiny needle, right? So if you slow down, and the needle is attached to the mill, right? So the mill is going to concentrate. So the needle is just following you behind like that. You're a bit of a lazy horse, you slow down, the needle pokes your backside, you accelerate again. This is a very simple feedback mechanism, right? This is an on-off mechanism. Now, the question you might ask is like, A, would that work? And under what conditions? Because actually, you can already imagine a very good reason not to do this kind of thing, right? So that's, imagine the horse stops a bit brutally, right? So just stops, and it gets poked so hard that it just runs away, and it pushes against the mill. So now the mill is having another quick impulse. So the needle is catching up with the horse as quickly as it was running away from it. So suddenly it's being poked by the needle again. The horse is panicking. He's going faster and faster, getting poked harder and harder. Basically, this is a runaway process, right? If the horse gives it too big an impulse, then the whole system is going to go into a frenzy, right? So this system would work, but only at the condition you had a reasonably well-behaved horse, right? A horse that sometimes slows down a little bit, gets a small poke, and goes, okay, fine, back to work, right? What does this simple example tell you? That actually, even with a very simple feedback system, there is that question of stability, right? Are there certain conditions under which this thing is just going to go catastrophically wrong? And obviously, also cruel for the horse and bad for the mill. Right, so this was a kind of very early idea about feedback. Pretty quickly, more elaborate ideas came into play, right? So one of the big revolutions in the 19th century, as you all know, was the invention of the steam engine. Now, what most people don't know is that Watt wasn't really, he very much didn't invent the steam engine. What he did was he invented all kinds of little upgrades to the steam engine, right? So one of them is this thing that you might have seen if you've seen any kind of steampunk films and things like that. You always have these two little balls which keep spinning around, so this is the thing you're seeing here. This is known as a Watt governor, right? And this thing is actually a feedback mechanism. How does this work? Okay, so you've got a steam engine. You're feeding coal into the steam engine, temperature increases, and brings your water to the boil, the vapor puts into motion a piston, etc. So this, you probably are all vaguely familiar with about how this works, But the problem is that, you're shoveling coal. This is not a fine art, right? You really are, the temperature of your, the temperature of the steam is going to vary, the pressure is going to vary, so you don't really have a simple way of just saying, well, you know in a rough way that if you add more coal, the pressure is going to increase, but it's certainly not a very precise mechanism for controlling your engine, right? And you want your engine to go at a constant rate, right? These first steam engines, they were used as pumps, right? And the pumping really needed to be fairly regular. So it can't be subject to random variations because, someone forgot to shovel coal for 2 minutes, or because someone was using a bigger shovel, right? So you need some way to stabilize the pressure of the steam that is used to work the pistons, right? And this was one of Watt's ideas earlier. One of his early ideas was called the governor. So this thing works in a very simple way. Basically, this thing is coupled to the engine itself. So the engine dictates the speed of rotation of this thing. But as you may know, if you've ever seen these kind of attractions where you have seats hanging from the top of a thing that spins, and as it spins, the seats go like that. So I don't know if you're all familiar with that kind of attraction design, right? So it's so thing spins, centrifugal force pushes the seats away. Well, same things are going to happen here. Basically, as the governor spins, the little arms there are just going to go like that. So the faster you spin, the more the arms are going to lift. If you slow down, they go back down. Now the thing is that this works a little bit like a corkscrew actually, is that as the arms lift, so if you go too fast, the arms lift, and they shut down a little valve here. So the arms lift, the valve closes, which means that less steam goes into the system. You're decreasing the pressure. As the pressure decreases, the engine slows down again, the arms go back down, and as the arms go back down, they reopen the valve, right? So this already, this is a neat little feedback mechanism, right? If you're going too fast, it closes the valve and reduces the pressure. If you're going too slow, the arms come down, the valve is opened, it increases the pressure. And you can also see that this thing is going to oscillate a bit, right? This, you can already see that, right? Because if it goes too fast, it'll go up and then back down, then up again. So there's going to be a kind of oscillating about the equilibrium position, which we'll see is one of the problems with this design, right? There are ways in which you can minimize this problem, but that was an early criticism of this governor of Watt's. Okay, So the point here is that this is actually a very simple mechanical feedback loop, right? There's no electronics or anything in there. Today we would use an electronic system, right? When I talked about earlier about the sensors and the actuators, like these would be, you know, these would probably be digital systems, right? But it also works with something completely mechanical, right? So, you know, even in the case of the donkey with the goad, that's even simpler than that. But this system already asks you some more interesting questions, right? Because this system allows you to really think more precisely about stability and about transient response times. Because ultimately, the question we're going to ask is, if I perturb the system, how long will it take before we go back to the value that we want? So imagine, this is the escalator again, right? So initially, the escalators, you know, basically the escalator's switched off. I switch it on, and my question is, how long will it take for the feedback mechanisms to come into play and to stabilize the escalator's functioning, right? So you can imagine this thing. So this is a step function, the green thing, either as being we've switched on the escalator, or just as a perturbation, right? The escalator was already functioning, but someone stepped on it, and therefore, you know, it perturbs the system, and we want to see what the response will be. Okay. So same thing as with the governor, right? So you can imagine a type of response where the feedback responds too sharply, so it overshoots. It overshoots, but then, you know, it comes back down, and eventually, in the case of the governor, you understand why this thing is dying off, right? This is the transient response, and you can see in the governor's case what's happening here is just, you know, its arms are moving, but they're rubbing against these little things. So eventually, friction will mean that any transient response will die out. This is what's happening here, right? So overshoot, undershoot, overshoot, undershoot, but ultimately, this dies out, it goes here. So this is the case of a system that isn't too damped. So we haven't, the friction on the arms is reasonably small, which means that we have a problem, which is that there's this overshoot here, which might actually be dangerous for if we want really a precise system. But on the bright side, what it does do is it reaches a value very close to the one we want. Here, this is the same system, but this time, we've introduced more damping. So this time, we've just, you know, we've made the little governor a little bit stiffer. So advantage, it doesn't overshoot as much, and it converges, basically, you know, it doesn't oscillate as much. But there are two problems here, right? Is that A is going to take longer, so as you can see, it approaches the correct value over a longer time scale, and also, it actually creates a static error, which means that actually this system, when it's heavily damped, it's not actually going to ever return quite to the correct value, right? So this gives you a sort of rough and ready idea of what we want an engineered feedback system to do, right? So the control system, it should be fast. So we want the time, the transient to be as short as possible, because obviously we want to limit the amount of time spent outside of the allowed value for the system response. So it needs to be fast. This one's fast. It needs to be accurate, meaning that we want the final value to be really the desired value. So this one is not very fast and it's not very accurate either, right? But there's another one, is that we want it to be stable. We don't want these oscillations, right? We don't want these oscillations, and worse, there are worst case scenarios where under certain conditions these oscillations don't ever really die down. So if the oscillations just kept going on forever, you'd have a system that was unstable, right? Because it would be the example of the escalator, right, where, you know, someone comes off the escalator, and instead of just adjusting the speed, it'll just overshoot and undershoot constantly, and, you know, and everyone on the escalator gets seasick, right? Okay. So these are the three things that you want from an engineered system with a control system. The problem is that as often, I don't know why that's the case actually, but it seems that quite often in life when you have three choices like that, at least two of these will be mutually incompatible, right? So it turns out you can't have all three. No control system will allow you to have all of these three perfectly. Basically, it's the rule of thumb is, you know, pick two and forget about the third one, right? It's like if you're going to be fast and accurate, so this is fast and accurate, but it's also not very stable. This definitely overshoots. And you can see really, the faster the response is going to be, the more it's going to overshoot, right? If I decrease the damping here, I'm going to get a response that's faster, but it's also going to overshoot more. And we know that that's potentially dangerous, right? You know, these oscillations can really severely damage your system, right? So if you want fast and accurate, you won't be stable. If you want stable and fast, then you're not going to be accurate, right? So you could make this one, you could make it faster, but you would also be increasing the static error, right? This difference here. Okay. So these three conditions in an actual engineering system, they'll never be really realized at the same time. So what happens, so the question becomes, okay, in a system which has feedback, what happens when you trigger an instability, right? Where you've entered a regime where these oscillations don't die down, for instance, or where, even worse, you can imagine a system that's so poorly engineered that it goes like that, right? Where initially you have a small error, and that small error gets amplified until the whole system goes into wild fluctuations. So this might seem far-fetched, but actually, you know, the example with the horse, that can do that, right? That horse, under certain conditions, will start to go into a frenzy. So the question is, okay, we have, if we had a linear system, then if the perturbation keeps increasing, it can actually increase forever. There's no limit to the growth of the perturbation in a linear system, because you remember, in a linear system, response is just proportional to the driving force. And this is the point at which nonlinear system behavior will kick in, right? Is that actually we know that eventually things don't blow up to infinity, right? And now we're going to see why it is that things don't blow up to infinity, which is precisely because of nonlinearity. Okay, so this is a very simple example which I've showed you a certain number of times, which is just a pendulum, right? And you remember the pendulum is interesting because at short amplitudes of its oscillations, it's actually linear. It behaves like a simple harmonic oscillator. So if you have a bob on a string and you just push it a little bit, then actually the amplitude at which you start the oscillations does not modify the period of oscillations, right? Something that Galileo discovered way back in the 17th century, I think. Okay, so it has a linear regime. And within that linear regime, you know what happens, right? If you were to swing this little bob at just the right frequency, right? At its resonant frequency, then eventually, you know, you're transmitting more and more energy to the bob and it'll swing wider and wider. So if you kept the linear theory, your equations would tell you, well, eventually the amplitude of the bob will be infinite, right? And you're perfectly well that's not really the case, right? But the question is, why isn't that the case yet? Why is it that in reality, if you swing this bob with its resonant frequency, eventually you won't be having like infinite amplitudes, and that's because it enters the nonlinear regime, meaning that as the amplitude swings, as it swings wider and wider, well, the sine theta terms, so the nonlinear term, becomes important. And when the amplitude is large enough, it means that the frequency of oscillations, and therefore the frequency at which driving is most efficient, that will start changing. And as this resonant frequency shifts and the amplitude increases, that means that the driving is no longer quite as effective, right? So there's a kind of like nonlinear sort of guardrail which says that your system, when it's linear, can display behavior whereby it will, its response will grow to infinity. But in reality, when the system goes far enough from being linear, the nonlinear behavior will constrain the response of the system. Which is basically the reason that any kind of like physical or like biological oscillator has to be nonlinear to some degree, right? Is that you want it to be robust, right? So you want it to be able to function at a very wide variety of rates. You want it not to be subject to, to the kind of instabilities that a simple linear system has. So nonlinearity in most cases is your friend, right? Because for instance, if you're talking about, a heart needs to be able to pump blood very accurately for years and with very varying rates, right? So your heart rate will go from say 60 to more than I don't know what the maximum is, probably certainly more than 100, but I don't know. Does anybody have an idea what the maximum heart rate is when you're sprinting or something? No biologists in the room. Okay. So this is an oscillator. It's a driven oscillator. The way your heart works is that it just kind of like gets electrical signals which make it contract. And if it were a linear oscillator, then it could be subject to instability in the same way that the feedback systems had instability, right? But as it turns out, because of its nonlinearity, your heart is actually a fairly robust system, right? It can actually take all kinds of perturbations in stride. But the drawback is that because it's nonlinear, it also occasionally displays chaotic behavior. So there is a certain regime of parameter values for your heart, which will just drive it into nonsense behavior, right? Which is what happens when you fibrillate, right? When your heart just kind of like stops beating in the coordinated fashion, it just becomes a mush. I don't think that's I think medics actually use the term a bag of worms. And this one was the other example, right, with the circadian rhythm, which is another example of biological oscillator. And that too has to be fairly robust, right? Because ultimately, the length of days will shift. You can move from one place to another. Have all kinds of variations to this rhythm. So it needs to be able to adapt to many different types of conditions. But again, under certain conditions, it can also go into chaotic behavior, which is this is actually a hypothesis that jet lag is actually due to the chaotic aspect of the circadian rhythm. Okay, so kind of to recap in the last minute. A complex system has many interacting parts, actually not necessarily many, so this is a caveat. And feedback mechanisms are really the thing that allows you to regulate the behavior of such a system. Feedback, it can stabilize or destabilize. Usually, negative feedback will stabilize, positive feedback will destabilize. And this is something that I do want to emphasize, is that as we've seen, nonlinear behavior does not necessarily mean that things are unstable, right? Linear systems can be unstable, and nonlinear systems can, on the other hand, be more stable than their linear counterparts, precisely because they're not subject to runaway perturbations, right? Okay, and the idea is that we now have a sort of rough and ready definition of what instability means, right? If we go back to our engineering examples, and unstable means that if you have an initially finite perturbations, say, the horse is just pushed against the mill thing, well, the thing that drives the mill, so it has a finite initial perturbation. We want a finite response, meaning that eventually any kind of transients get damped out, which is not the case for the unstable horse system, right? Because the horse keeps, it tries to run ahead, gets poked, runs ahead again, and it's just, its response will never die out, right? It will always keep going to that frenzy, until eventually, I guess, it gets hungry or something. Okay, in a linear system, a perturbation like that can grow without bounds. So this is what we've seen. One of the reasons that linear systems are not actually particularly robust. Whereas in real systems, there will always be some kind of nonlinearity that comes into play. And you're going to remember, even with the simple harmonic oscillator, you remember that system which is just a bob on a spring, which just oscillates like that? Well, you know that eventually this will also go into nonlinear behavior. For instance, as you pull the spring too much, the elasticity of the spring will decrease. So nonlinearity will always prevent the divergence of the response, meaning you will never get an infinite response from a finite system precisely because of nonlinearity. Okay, and so this is a kind of like take-home thing, is that nonlinearity is a double-edged sword, right? It makes systems more robust to perturbations, but also in other circumstances it makes the system prone to chaos, right? Because as we saw, we saw that with the logistic map. We saw that as well with the weather system, right? The weather system can display all kinds of like chaotic patterns if you change certain parameter values. Okay, that's about it for today. Tomorrow we'll actually have a look at precisely how a system becomes chaotic. So this will be more about what's known as bifurcations, and in particular about why it is that most chaotic systems look alike, despite the fact that they might describe very different systems, right? So we'll see that, for instance, population dynamics, weather, certain types of phase transitions in physics, these are very much described by, these have very different models, but display the same kind of broad characteristics in their behavior, and we'll see why. This is something which is known as universality in physics, and it's a very interesting topic. So this is some reading if you want to have a go. The Dynamics of Complex Systems, this is a very, very big book. It's good for two things. It has a broad introduction to complex systems as a whole. This is where I got the definition from. It also has a bunch of interesting special topics. So if you're interested, for instance, if you're particularly interested in, applications of complex systems to, cellular automata or to biological self-organization, this is where you'll find it. This, by Tim Lenton, is basically where I draw most of the examples from Earth system sciences. History of Control Engineering, this is where I found the donkey thing. And Chaos by James Gleick, as usual, is just a very compelling read. So if you have time for one book, read that one. I mean, basically, all the you'll find most of the interesting kind of like anecdotes and applications of chaos. They will come mostly from that book. Okay, well that's pretty much it. Do you have any questions? Yes. Yeah, go ahead, and then you.
So we just go with the engineering history slide with reference to the compromises, like if that's possible.
Oh yeah, sure. There we go. So basically, imagine this is the response of a system to a perturbation. You know, you've turned on the system. This is what you want the system to behave like, right? So you've switched on the escalator. You want constant velocity. What happens in reality is that your feedback systems come into play, and they lead you to overshoot a little bit at the beginning, and then as the system tries to stabilize to a given value, these oscillations die out. And the idea is that you can modify, depending on what kind of feedback system you're using, you can modify certain parameters of the feedback. So remember so if you're looking at the Watt governor, for instance, you can modify friction in the arms here. You can modify the inertia of so the weight of the balls, and that will give you different types of feedback, different types of response. And the idea is that fast response means that you respond to the switching on quickly, right? And you cross that line very early on. So that's fast, right? This is less fast. Accuracy just means that your steady state solution is as close as possible to the desired value, the green line, right? So this yellow line, this one's accurate, and it's also fast. This one's not very fast, and it's not very accurate. But what this one doesn't have is stability, right? So stability is just how much will this thing oscillate around the desired value. And ultimately, you don't want things to oscillate too much, right? That's just not a very good feature in an engineering system. Does that clear up the?
Just go over the history slide too.
Yeah. This one?
The other one.
This one?
Yeah.
Yeah. So this is the Watt governor. This is a steam engine. So the idea of a steam engine, right, is you have pressurized steam that makes the piston move up and down. And the question is, how do you regulate the pressure of the steam? And a possible answer is what's known as the governor. So the governor, what it does is, this is just a spinning part, right? So the machine here, the steam engine, makes the governor rotate. If it rotates too fast, the balls here lift. If the balls lift, the valve closes. If the valve closes, then the system slows down, pressure diminishes, and inversely, right? If it slows down too much, then the balls drop, the valve opens, the system goes back into increasing its pressure. Yep?
I'm just trying to understand, in a complex system where positive and negative feedback coexist, how does the system make sure that these two aren't counteracting each other? Because on one hand, the system is being stabilized, but then the positive feedback is also going to be stabilized.
Yeah, so that will basically depend on the response times, right? Because if we go back to the example with the carbon cycle, you saw that there was, on the one hand, a positive feedback loop, and on the other hand, a negative feedback loop. And what actually happens is just that one of these loops will stabilize the system, but over 100,000 years, and the other ones acts over, say, 1,000 years. So ultimately what's going to happen is that at first you'll have the destabilizing effects of the positive feedback loop, and then eventually all of this gets stabilized in the long run by the slower system. But this is something that is a perennial worry, right, in Earth system sciences, right? Is like which systems are coming into play, how fast, do we need to look, are we looking at climate timescales, so timescales of hundreds or thousands of years? Are we looking at geological timescales, hundreds of millions of years maybe? And this tells you, this tells you which subsystems you'll be interested in, basically.
And so do we have systems which only respond to negative feedback and are ineffective to positive feedback?
Mm-hmm. Yeah. So the silicate weathering, for instance, this one, is pure negative feedback, right? This one responds always by trying to get back to a kind of constant temperature, right? This one will resist any change in temperature. This is a pure negative feedback loop.
So this will be ineffective to positive feedback?
There's no positive feedback in there. This one's pure negative feedback, right? Because what it does is that any change in temperature will eventually lead to a change in temperature in the opposite direction. So if you increase the temperature at the start, you'll decrease the temperature at the end. If you decrease the temperature at the start, you'll increase the temperature at the end. So this is, this is probably the main mechanism for understanding the Earth's fairly stable temperature over hundreds of millions of years. But this is a very slow system, right? This isn't, you can't count on that over time spans of hundreds or thousands of years. This is like hundreds of thousands, millions of years. Yeah, sure.
When you say that the non-linear system is not unstable,
yeah.
Does that also mean that it's not chaotic?
No, so this is the thing. So a nonlinear system is not necessarily unstable. Some of them can be unstable, but nonlinear systems can very much be chaotic. Basically, these are different. These are not necessarily quite the same thing, right? So instability has a very simple definition, right? Instability means I give you a finite, push, and you respond by oscillating forever, for instance. That's unstable because it means I've given you a finite amount of energy and you respond by behavior that is basically infinite, right? It keeps going on forever. So that's instability. Chaos will happen in nonlinear systems. But chaos is not so much instability as it is kind of unpredictability, right? You have for instance, sensitive dependence on initial conditions, or you can have, where we were talking about parametric instability, or at least structural instability, where a small change in parameters just changes the entire nature of your system. We'll go back, this stuff we'll discuss a bit more tomorrow, I think. But yeah, what I wanted you to take home is really not to confuse these two ideas, right? Unstable we can be talking about a linear system that's unstable. Nonlinear is a different, nonlinear just means that you don't respond proportionally, right? Unstable means that your response to a finite perturbation can be infinite, or unbounded, rather. Does that clear things up a little bit? Okay, well, hopefully tomorrow we'll clear a little bit more of this stuff up. Also, I've been asked by quite a few people about the slides, so I will give them to Ravi, who will put them up on your e-learning online thing. If anybody wants me to send them to them right now, you just give me your email address and I'll send them to you by hand. So basically, Ravi will take care of this, I think, by the end of this week. But if you want them now because you've missed a few lectures or something, then just give me your email address and I'll do it today, right? Okay, great. Well, thanks for your attention, and we'll see you guys tomorrow.